Olá, estamos iniciando mais um programa Nossos Pesquisadores. Hoje aqui na cobertura da Aula Magna de 2017 do Instituto de Física de São Carlos da Universidade de São Paulo, com o professor Daniel Kleppner. Nós estamos com o professor Vanderlei Banhato, um dos organizadores dessa aula magna, com o professor Kleppner. Ele vai falar um pouco mais da importância desse tipo de evento aqui para os alunos que estão ingressando no Instituto de Física de São Carlos.
Bom, uma aula magna, ela tem o objetivo de motivar as pessoas, tem o objetivo de dar uma visão de alguma coisa para as pessoas. Na área da física, as pessoas caminham motivadas. As pessoas têm que enxergar motivação, têm que enxergar motivos de paixão para poder perseguir determinados objetivos. E no caso do Daniel Kleppner, ele é uma pessoa que tem uma carreira de muita motivação e que, portanto, deve transmitir aos alunos um pouco dessa motivação. Em ciência sempre é importante a gente ter os mentores, aquelas pessoas que nos guiam, aquelas pessoas que foram a chave para a gente tomar decisões. E eu acho que o Kleppner é uma pessoa que leva muito a sério, pelo número de alunos que ele já formou, pelo volume de pesquisas, os prêmios que ele ganhou e os prêmios Nobel que ele produziu. Então, é uma pessoa do MIT, talvez um dos físicos atômicos mais importantes da atualidade, né? E que deverá dar uma mensagem importante para quem está começando na carreira. Quer dizer, como são as coisas, como devem ser e como os alunos ingressantes numa carreira tão bonita como essa que é a física devem enxergar isso.
E o professor Kleppner já é um professor da casa, né? Ele já tem um relacionamento com o Instituto de Física de São Carlos há algum tempo, né?
O professor Kleppner, ele é um professor honorário do Instituto de Física de São Carlos, e ele vem periodicamente para o Brasil e tem um relacionamento com o Brasil e com São Carlos em especial muito grande.
Ok, obrigado por você.
Só quero dizer para vocês que a aula magna, ela é o início, que o nosso vice-diretor vai dizer, e ela tem que ser motivacional, né? Ela tem que ser temas que podem despertar o seu interesse. Nós físicos vivemos de motivação. Às vezes a gente tem uma motivação íntima muito grande, mas em 99% dos casos, a gente observando pessoas e a opinião delas, desenvolvemos as nossas motivações e as nossas paixões para levar a ciência adiante. Então, a mensagem de uma aula dessa vai muito além da física que vai ser apresentada. Claro que uma das coisas mais modernas é a parte quântica, né? Ele vai dizer, numa linguagem bem coloquial, os conceitos, as coisas que estão mudando a nossa forma de enxergar o mundo quântico, mas vocês devem enxergar além, tá certo? É o que você pode tirar de mensagem, é o que você pode construir a motivação para essa carreira que nós escolhemos, né? Eu escolhi muito tempo atrás, alguns colegas daqui e agora vocês. E acredite, a gente é movido por aquilo que está dentro da gente. Nós temos que toda hora criar um monumento dentro. E a gente vai, então, lapidando esse monumento. E a motivação é fundamental. Então é por isso que a gente fez o esforço de trazer um físico e um expert em motivar as pessoas, pelo número de pessoas que ele já colocou em física. Tá certo? Vou chamar o professor Richard Garrato, que é o nosso vice-diretor, para dar início às atividades.
Obrigado, Vanderlei. Bom dia a todos. Meu nome é Richard, para quem não conhece, que deve ser a grande maioria aqui, com certeza. Mas é muito bom ver o auditório tão cheio para, então, assistir a aula magna do ano acadêmico 2017. Como o Vanderlei falou um pouquinho agora há pouco, sobre a importância da aula magna, basicamente representa o início das atividades acadêmicas do ano. E por isso a gente busca trazer sempre alguém que de fato vai motivar vocês, vai contagiar vocês com seu próprio entusiasmo pela ciência desenvolve. E, evidentemente, esse ano não é uma exceção em relação a isso. É um grande prazer, é uma honra para nós recebermos de volta ao IFSC o professor Daniel Kleppner, do MIT, Massachusetts Institute of Technology, que já esteve aqui conosco uma meia dúzia de vezes ao longo dos últimos 30 anos. E eu tenho certeza que no final da palestra dele vocês vão estar totalmente convencidos de que vocês tomaram a decisão certa de optar por física, vindo aqui, juntando-se a nós nesse empreendimento mundial, que é aquilo que cientistas fazem, que é desvendar os mistérios da natureza e do universo. Não tem nada melhor para você fazer ao longo das poucas décadas que cada um de nós tem na face do planeta. Com certeza, a palestra do professor Kleppner vai servir para convencer vocês que vocês estão no caminho certo. Mas agora eu vou mudar de língua e agradecer a presença do professor Kleppner em inglês. So, I always get a little bit nervous when I have to speak English, because people expect me to do it well. That is not always the case. Anyway, I would just like to spend a few words saying thank you once again to Professor Kleppner. I know you've had a tough journey to get here and only a few hours sleep last night. We really do appreciate your presence with us. We're absolutely certain that your talk will be a stimulating talk, which will motivate our students in there, and they will remember it probably for the rest of their careers. Actually, it's not just a question of welcoming Professor Kleppner to Física. I would say we're welcoming you back, because in a sense you are one of us. Probably most of you don't know this, but Professor Kleppner is one of only 2 honorary professors of the Institute of Physics here in Seoul campus. So in a sense you're one of us, and we're welcoming you back home. Nobody more appropriate to give the Aula Magna, the inaugural lecture for 2017. Vanderlei, did you want to say something more about Professor Kleppner's scientific career before we actually finally allow him to say something? Thank you.
Okay. Thank you, Richard. Richard is afraid to speak English. I am always in panic. Because I know that I'm going to do some mistakes. But I will just introduce you Professor Daniel Kleppner. And for me, it's hard to introduce Daniel Kleppner because I've been speaking about him my whole life. He is a mentor, he was a mentor for me and for other people in Brazil. I think Brazilian students doing physics at MIT met Daniel Kleppner and got the enthusiasm that he can pass to us. And so I've been speaking so long about Daniel Kleppner that I don't know if I can now say in a compact way 5 minutes of his career. Daniel Kleppner is an American. I think he did his high school in New York.
Near New York.
And already in high school, he got some very important mentors that was telling him indirectly that his talent was physics. I don't know if you believe at that time that your talent was physics. It seems that you didn't know exactly in high school. You think it is a secret. But some people in his life, in high school, were fundamental for him to take that decision. They give him the right motivation. And then he decided to study physics. And at that time, physics had a lot of different challenges. But he was motivated enough and moved to England for his bachelor. And got his bachelor degree. And doing his bachelor degree, he also met people that was mentor to him, that drive him to the right direction. And I learned from him that you hear about Norman Ramsey when you didn't know him yet. And you read his book about nuclear momentum. And then his professors, the undergraduate, told him, "Oh, that's a field to go. Let's go atomic physics." And then, after finishing, he decided to do his PhD. And then is when he landed at Harvard University. And surprisingly, walking the corridor, he found the name of Norman Ramsey. And then I said, "This is the guy." And then he started to study his PhD with Norman Ramsey. That's Nobel Prize in 89 in physics. And one of the key persons for atomic clocks and hydrogen laser. He did a thesis, and he basically invented the hydrogen laser that today is a very important device in all the telecommunication, navigation, and so on. After finishing his PhD, he decided to continue on this, and he was hired as assistant professor in Harvard first, and then a full professor at MIT. And at MIT, then Kleppner did work in fields that today are very fundamental for us to continue to understand the quantum nature of matter. So he started the field of, he was one of the pioneers at least, in Heidelberg atoms. Heidelberg atoms are atoms very high excited, that tell us a lot of things about how things are going on between electrons very close to the nucleus and very far. And he studied, I think, the first time the establishment of a chaotic type of effect in the levels of the quantum system. He also was the starting person for quantum atoms in heavy, quantum electrodynamics. And ended by Serge Roche taking that and getting Nobel Prize 2 years ago. And I think Serge Roche was working with you for a while. Right? And Serge Roche came here 2 years ago too. But that's not enough. Then Kleppner also works in field of precision. You see, we don't, when we learn in school the fundamental constants, we learn, oh, velocity of light is now definition. Sometimes we forget how much science is behind the determination of fundamental constants. In fact, it's not to exaggerate to say that to determine the precision of nature is the main source of evolution of our knowledge in physics today. Trying to measure well things is what made physics evolve the way it has been done. And then is being one of the seminal persons in this field. Right? He's, I would say, one of the men behind the atomic clock. But that's not enough. He also worked in the beginning of the quantum gases. We all learn quantum mechanics, and we say, why we don't see that by eyes? In some situations we do, which is many different effects. One of them is the Bose-Einstein condensation. And then Kleppner was of the brave scientists that say, I want to do Bose condensation in hydrogen. And he started to produce people. Some of the people he produced in his lab did the condensation before he did. At Cornell, Wolfgang Ketter, Andy Hewlett. At Cornell, Andy Hewlett got Nobel Prize. And Carl Wyman was also in your lab and also got Nobel Prize. David Weiland is also related to you through Norman Ramsey and also got Nobel Prize. So Dan has touched so important fields that today people appreciate so much that he got all the prizes that a physicist can get. I'm not going to read all the medals, But this year, 3 weeks ago, a month ago, it was in January, the APS, he got the most important prize in the United States, which is a prize they give you for recognition of the overall work you have done in physics. So he's one of those recipients. He did not get Nobel Prize yet, but he tells us that doesn't matter. And it really doesn't matter because he didn't get one Nobel Prize. He got 6. 6 of his students or people that passed his lab or is related to him got Nobel Prize. I think you then walk to the Nobel ceremony more than any Nobel Prize that we know. And of course, he is one of the legends of MIT in physics. He started many important fields. He worked with people that, if you see the names, there are people that even today we study the books. And so we thought it was a great idea to bring them to tell you a little bit about the history of all this and what's still left behind for us to do, which is some of the things you have to learn. That is one important thing with that Kleppner. He believes that you have to have mentors. You have to watch people. You have to get example in science. And you know that. You've been my example for many years and always accepting invitations and always receiving us, not only me, but many Brazilians that go to MIT. And we appreciate very much you here. And please, you have the time now to give your lecture. Thank you.
A gente vai para um breve intervalo e já está de volta. Estamos de volta aqui com o programa Nossos Pesquisadores na Aula Magna do IFSC 2017.
What I wanted to say is that over these years I've watched the university develop. And that's been a great pleasure. Now there is such wonderful physics being done here that it is always a joy to visit. I also enjoy visiting because people here are so friendly and the food is so good. And I always think of Brazil very warmly and of this institution very warmly and Vanderlei very warmly. He's an institution himself. Vanderlei told you a little bit about my career and the importance of mentors, good teachers, and they've been very important to me. My high school teacher was Arthur B. Hussey. He taught me in my senior year. That's the first time I really encountered physics, and he was so inspiring. I left knowing that I wanted to be a physicist. That's very helpful. You know what you want to do at an early age. Along the way, I had sort of other ideas, learned about other things, but it's always been physics. In my college, a little college in Massachusetts called Williams College, a liberal arts school, they had a very fine physics department, and the teachers there were very kind to me. I wanted to do a project on my own, and they gave me laboratory space and spent a lot of time explaining electronics to me. So I had a good deal of experimental experience as an undergraduate. Then I went to Cambridge University for 2 years as an undergraduate. And in my second year, I had a very wonderful young physicist, Kenneth Smith, who told me about the work that he was doing. And I think that's a good place to leap off to what I'm really going to talk about now. I'm going to talk, it's basically about my research. And this is kind of distorted because there are so many things have been going on during that period, so many wonderful advances. So I'm just talking about a few of them. And so many people collaborated with me and worked with me that I can't start to list them all. So please don't get the impression here that I'm the man who did everything. I'm the man who directed the students who did everything. Now, this field which I call quantum science is basically the science which has emerged since the discovery of atom cooling and cavity QED. These first emerged about 30 years ago. They started to develop. And the field has exploded now. It is, well, the best example of that explosion was this award the American Physical Society gave me this year. This award was selected by representatives of all of the divisions of the American Physical Society. And what it does is to recognize that this field itself is now a forefront field and one of the most exciting fields in physics. Last year it was given, and for the first time in theory, for the creation of string theory by Ed Witten. This year they gave it for the creation of what I'm calling quantum science here, for this body of work which has stimulated so many people and has caused such excitement. And I would like to show where some of that came from. I know that most of you here are just starting out in physics. And you may be wondering how you ever get to where physics is really done. It seems so remote, so far away. How does one do physics? Well, I'll give a few examples of how these ideas grew and how important it is to talk to others, to interact with others, and to keep your eyes open and to have the right combination of courage and foolishness. So I want to go back to the beginning, since most of you do not know that much about modern physics. So it begins with a famous experiment done in 1922 by Otto Stern and Walter Gerlach at the University of Hamburg. Stern was pioneering a subject called molecular beams. This is physics you do by letting a stream of atoms go through a high vacuum so they can move without reflection. And what he was doing was studying the properties of atoms which had little magnetism to the electrons going around, basically form a little magnet. And because of that magnet, if you put them in a magnetic field, the magnets, they try to align along the field, but because of their angular momentum, it's just like a gyroscope which recesses around. People were just amazed that they're coming around for the first time they had to take quantum ideas seriously. So this experiment launched the golden age of quantum mechanics and followed very quickly with the works of Einstein. It's interesting, Einstein and Stern were friends, and Einstein took an interest in Stern's work and sort of advised and collaborated with him. Now, this young American, he was using this deflection then. This is a Stern Gerlach magnet there, and another one there, pointing in opposite directions, and deflecting the atoms first one way and then another. With this, well, by looking at these deflections, you can find out about the nuclear properties. Allowed Robbie's idea of an atomic clock to become a reality. I'll explain a little bit about what it means. What it means is, I said that the longer the atoms spend in interacting with the radio frequency field, essentially the longer the time you're making the measurement, the sharper it would be. And Ramsey wanted to make the machine do longer and longer and longer. The transitions he was looking at depended strength of the field, overall, you get a somewhat sharper curve there. So we thought that was very exciting. Immediately put it to use in his lab. And then it only became apparent later how really important it is, because it's the basis of, I can't say most atomic physics today, but much of it. With quantum solution, we think of the system as an interferometer. You have an atom coming in one state here. Over here, you put it into a mixture of states. And over there, you unmix the states, if you like. You get an interference pattern between here and there. So that's just a different language. But what's very interesting is in between, you don't know which states the atoms are in. 60 years later, that would be 6 factors of 10. The first clocks were roughly 10 to the 16th, 10 to the 10th accurate. The ones today are about 10 to the 16th. So that has been a very nice chapter, but what has come out of the atomic clocks is something nobody dreamed about. What's come out of the atomic clocks are the global positioning system. Now, the global positioning system just is incredibly important. It's a great boon to mankind for many, many reasons, in addition to being able to drive around town more easily. It turns out everyone can drive around town more easily. Nobody can drive around town more easily, but it's still very nice to know where you're going to go. If one were to go to Congress to try to explain why it's important to do basic research, you can't think of a better example than this. If you went to Congress and say, I want money to study Einstein's theory of general relativity. Well, Einstein's theory of general relativity is about the least practical theory you could ever think of. And I might say that when we were, the motivation for these clocks, as I've showed from Robbie's talk, from my own experience, and also from Ramsey, was to measure this gravitational redshift. It was purely basic research, but what's come out of it is this fantastic new technology and new industry. Well, going on to my own work with Ramsey, let me just mention that in 1954, Towns really invented the maser. The maser is another type of device for doing microwave resonance on atoms and molecules. In the maser, you take a stream of atoms, you select them in one state, and you let them go into a resonant cavity. And if some of them start radiating, then the field in the cavity builds up and the others will too. And it's an oscillator. The atomic clocks I've been explaining are passive devices. You have to apply a signal. The reason I'm showing this is a page and a half in the Physical Review. And this is a picture right here. There's a source of maser. This is atoms or molecules. This is a state selector, and here's just a cavity, and here's a signal coming out. They explain the principle of the maser, the theory of the maser, the construction of the maser, and they give experimental results, and that's all in 1.5 pages in the Physical Review. And I like to quote this as an example that if you write clearly, you can write briefly and say an awful lot. Anyway, this is a maser that Norman Ramsey proposed. It works on the hydrogen atom. It's the same idea. You have a source of atoms over here. You choose atoms in just the state that you want and go into a microwave cavity. Thinking about that when I came along, so I started working with him. I did an experiment just to see whether atoms can bounce at all and still maintain their state coherence. Turns out they could, and with that knowledge we went on and built the hydrogen maser. And the hydrogen maser has turned out to be a very useful device. Yeah, this is a picture from the original publication of it, but it shows just as where a system can be doing two things at once. And this idea of entanglement is now crucially important to the subject of quantum information theory, quantum measurements.
A gente vai para um breve intervalo e já está de volta. Estamos de volta aqui com o programa Nossos Pesquisadores na Aula Magna do IFSC 2017. Bom, eu estou aqui com o
Rafael Garcia.
Você é de onde, Rafael?
Sou de São Bernardo do Campo.
Que curso você veio fazer aqui no IFSC?
Fazer Física, primeiro ano mesmo.
Ok. E o que você achou dessa palestra hoje, da motivação do professor?
Muito interessante, né? Assim, às vezes até a física que tá ali é um pouco mais complicada pra gente entender tudo, mas o que importa mais é toda a história aqui, certo? Então é uma ciência nova que está sendo envolvida e às vezes você tem que acompanhar tudo o que está acontecendo ao mesmo tempo para conseguir, entendeu? Puxar uma coisa dali, outra dali, para conseguir, entendeu? Esqueci a palavra, mas conseguir melhorar, né? Conseguir fazer mais descobertas, etc, etc.
E qual foi a sua motivação para vir aqui para o IFSC, para vir para São Carlos?
Olha, eu fiz a IFSC ano passado, Escola de Física Contemporânea, e depois que passei uma semana aqui, fiquei apaixonado pelo Instituto, né? Melhor que a Física de São Paulo, inclusive. Eu achei que eu conheço os professores, os laboratórios, as linhas de pesquisa até, e falei, não, é aqui que eu quero estudar. Foi isso.
Legal, muito obrigado e bem-vindo ao IFSC.
Obrigado.
Falou. Bom, eu estou aqui com o
Igor.
Igor, você veio da onde?
Eu vim de Botucatu.
E que curso você veio fazer aqui no IFSC?
Licenciatura em Ciências Exatas.
E o que você está achando dessa semana de recepção, da aula magna, desses eventos aqui?
A semana como um todo eu achei muito legal, a gente está só no começo, mas tenho bastante boas esperanças até o final. Os veteranos são muito legais, o campus é muito bom. É evidente a perder aquele medo da USP, aquele lugar onde você vê engenho e tal, a gente percebe que o pessoal é bem comum mesmo. Em específico a palestra eu achei muito legal, interessante, porque a gente conhece outras áreas, ou até mesmo a mesma área, mas assim, uma coisa que dificilmente ia ver no meu curso, por exemplo, mas que pode despertar a curiosidade de muitas pessoas também.
E como você descobriu essa vocação para vir aqui para o IFSC, para fazer licenciatura? Como você se decidiu por essa carreira?
Sim, desde pequeno eu queria fazer engenharia, só engenharia. Aí na feira da USP mesmo em São Paulo, que teve no ano passado, eu fui, achei muito interessante e acabei decidindo trocar por licenciatura mesmo.
Ok, legal, bem-vindo e obrigado. Bom, eu estou agora aqui com o
Emanuel.
Emanuel, você veio de onde?
Eu sou da Colômbia, mas eu trabalho no grupo do professor Vanderlei Banhato, condensado de Bose-Einstein.
Você está fazendo mestrado, doutorado?
Eu sou estudante de doutorado.
E o que você achou da palestra hoje do professor Daniel Kleppner?
Bom, eu achei muito legal porque o professor Dan, nessa área da física e, bom, geral, é uma pessoa muito importante e foi um discurso muito motivacional, falando da história, de quais são os grandes avanços, os grandes coisas que se han logrado nessa área. Então, foi muito importante que o professor Dan fosse falado isso, porque dá um gás para a gente para seguir, dá para motivar para seguir conseguindo coisas nessa área que é muito, muito legal.
E qual foi a sua motivação? Por que você escolheu a física? Por que você escolheu essa área de física atômica para fazer o doutorado? O que te motivou nisso?
Então, eu fui motivado pelo fato de saber como funciona, na verdade, a interação da luz com a matéria é muito interessante, pelo fato da matéria em si, mas também pelo fato de o que é a luz. A luz é uma coisa tão legal que se você tenta imaginar o que é você vai se encontrar num mundo fantástico de possibilidades. Então isso foi uma grande motivação para mim, porque no grupo do professor Banhato, no experimento, eu consigo tentar entender cada vez mais essas questões que uma vez eu fiz para mim. Então foi a minha principal motivação.
Ok, muito obrigado. Okay, now we are with the Professor Daniel Kleppner that just gave a wonderful lecture now today, and we'll do some questions. And the first one is, how important is the motivation for physics at the early stages of the education?
It's everything. The earlier one falls in love with physics, the better it is. The earlier one falls in love with science, the better it is. So I think that's absolutely crucial.
And how did you find this motivation?
Really from teachers. I mean, I like doing things, I like making things, making electric circuits and all the mechanical things one made in those days. But when I started really learning what physics was from a very gifted teacher, that convinced me that's what I wanted to be.
And what are, in your view, the new challenges for the young physicists?
Well, the world seems so much more complicated now than when I was young. But there are many routes into physics, and it's always been difficult to decide just what one wants to do. When I look in a modern physics laboratory in my field, the equipment seems so complicated, I wonder, could I ever learn how to use that? But of course students have. And then I go back and think about my own equipment, which was terribly complicated to build. You're always sort of pushing things. It's always hard work. And what's important is just the motivation and the enthusiasm and you know, the optimism.
And how you see the world in the near future, in the science? What will be the big advances in the science in the next few years?
It's always difficult to predict that. One you can predict, though, the discovery of the gravitational pulse is opening a new area. It's a new form of spectroscopy. I'm sure that will be productive. There are new things to learn. Certainly astronomy and astrophysics are flourishing now. But in this area of what I call quantum physics, it is still ballooning. No one knows where it's going to go. One indication that the field is in very promising shape is that there's so many good young people going into it. That's always a healthy indication. So I'm sure this field will flourish, but other areas will flourish too. I think it appears that neuroscience is on the threshold of making real advances, and probably other areas of biology and medicine are up for grabs. Mm-hmm. So there are lots of opportunities. My concern isn't lack of opportunities. My concern is whether the public interest is high enough to sustain it at the level it needs.
How you see the science in Brazil, the things that we are doing here?
Well, as I mentioned earlier, this university has really blossomed since I first knew it. I don't know that much other science in Brazil. Well, one of my students, Claudia Cesar, is at Rio de Janeiro, and he participated in this experiment which did the first spectroscopy on anti-hydrogen. That's a very exciting discovery there. So there's a little nexus of anti-hydrogen research right here in Brazil. So that's another advance that I know. But my interests are really rather parochial. I only know what's going on in sort of atomic and atomic, molecular, optical physics, or quantum science. And I think Brazil has a lot to be proud of.
And how was your impression of the student of this event today?
Great. For one thing, it was packed, which is a nice, and they did ask questions once they were given a little coaxing, which is a good sign, and there were good questions. So I felt what we call good vibrations. Okay.
Okay, thank you so much, Professor. Bom, e chegamos ao final de mais um programa Nossos Pesquisadores. Aqui na Aula Magna de 2017 do Instituto de Física de São Carlos, diretamente aqui do auditório, o professor Sérgio Mascarenhas. E eu sou o Sebastião Prata Vieira, pesquisador aqui do Instituto de Física de São Carlos, da Universidade de São Paulo.